Happy Thursday. I have to think. I can feel the excitement in the audience today. I can feel it.
Very excited.
Let's all take a deep breath. Let's get things started. I have an amazing question to start things, a student question to start things off. It says, "Dear Bob, happy Thursday." No. Don't be afraid to start your email that way. Just wondering with regards to the coursework if we can include more than one image for each visualization. For example, I've created a map visualization and you can interact with the data by zooming in and clicking each spot, and I would like to show this interaction. The answer is yes, definitely, and that's great news. And in the next coursework, you're actually going to use screen capturing software to take a screen capture of you using the software, save it as a video file and submit that. And you're allowed to do this, you're allowed to do that with this assignment if you want. It's not required, but you're allowed to submit supplementary video interaction files or animation files with this assignment on Blackboard. And in the next assignment, I'm going to hopefully make it a requirement. Hopefully. That's the plan. Any other amazing questions about assignment 1? Everybody got to meet the beautiful Richard Roberts on Tuesday, the people that went to the lab. Very talented student. And before we start with the slides, I thought I would mention you can find some amazing demos of tree maps in action and other information visualization methods on YouTube on the DataVis channel, right? So this one's called Interactive Tree Maps for the Visualization of Call Center Data, and Rich is working on this as part of his PhD. There's a voiceover with this video, so I'm going to turn down the volume for now. But basically, the idea is that he's using tree maps to visualize call center data. Probably you've all called call centers before. Yeah, you can't avoid them, really. So they're really important. It sounds very specialized, but actually there are something like more than 1 million people employed in call centers in the UK. And there are many millions of people employed worldwide. In Europe, there are more people employed in a call center than there live in Wales. So it's serious business, actually. So so one company has approached us, QPC, and said, "Can you help us visualize this data?" And that's exactly what Richard Roberts is working on. And this is an interactive tree map visualization. The top level rectangles or squares are mapped to call volume, so the number of calls that the call center received in the corresponding hour. So these are 24 hours. This is midnight down to midnight again. So you can see an overview of the activity, right? The biggest bunch of calls comes right at lunchtime, for example, and then they taper off in the evening. And color is mapped to the percentage of abandoned calls. And you can see immediately, oh wow, people start abandoning their calls in the evening a lot more than in the morning, for example. So I encourage you to have a look at that. It has a voiceover, so you can see the details, and there's a reference. So those are tree maps in action, or that's a tree map in action. There's a histogram, and there's a navigation tool and filtering tools. It's really good stuff. Here's another one, completely different application. This is visualizing translation data. There's that word tree, that interactive word tree that we mentioned before, and it's linked to a tree map. This tree map could be better. It's only showing one level at a time, which is not the ideal case. The ideal case, it would show 2 or 3 levels at the same time, but the idea is still nice, right? And it's linked together, so when the user clicks on a node, it's visualized in the tree map, and there's a tool here that lets the user interactively change the order of the hierarchy. So the hierarchy is arbitrary in a tree map, right? And then there's some other information, but that's another example of a tree map in action, in case you want to look at those. And those are produced by Swansea University students. That's the other exciting thing about that. Any questions before we start? Any other questions about assignment 1?
So if we combine a line graph with a bar chart, does it count as one visualization?
You could have that as extra credit, like combining a line chart and a bar chart. But you wouldn't get, that's not better than Professor C. It has to be better than Professor C. I can see there's a tremendous temptation to use bar charts and line charts and pie charts. I guess it's like overwhelming, isn't it? Like you feel like, oh, I have to use those. But you don't want to be like average, right? You don't want to be like just another person. You want to be extraordinary, above average, more sophisticated. We were talking about hierarchical visualization and tree maps. We looked at the software you can download. Did anybody download it and visualize their hard drive? You can get a Mac version, a Linux version, and a Windows version if you're interested. This is another tree map application visualizing the stock market. So where the blocks are mapped to the volume of trade. This is absolutely beautiful. I love this one. It's called the map of the market. I don't know if it's still online or not, but I remember the first time I saw this, I actually got to see this being presented live at a conference back in 2000. I think it was 1 or 2. I guess it was 2001, a long time ago now. But the green means that the stock price of that particular share is increasing. And the red means it's decreasing. If it's very green, it's increasing rapidly or it increased a lot, and the red means it's decreasing rapidly. The size of the rectangle is mapped to the volume of trade. It's such a great visualization. So healthcare, all the healthcare companies are grouped together, finance companies, automotive companies, and all the different sectors are grouped together. It's absolutely brilliant, this one. And you can see in just 2 seconds what's happening in the stock market. Just in 2 seconds, like, oh, I know in 2 seconds. Does anybody know the traditional way of visualizing stock market activity?
Graph.
Line plots?
Line
Yes.
graph.
Any other ones? Reese?
A textural list with colours indicating increases and decreases.
Exactly, that annoying scroll bar at the bottom that you try to read the 3-letter symbol that's passing really fast along the bottom. Like, and then maybe there's an arrow going up or down and some numbers and it's zooming by. That's the traditional way, in a line graph of one company at a time. So this is a million times better. This is an example of tree maps combined with other views of data. So that's a tree map view. And this is scientific. This is a spatial view of flow. And one of the problems or challenges in scientific visualization with this kind of data is picking and choosing clusters. Like, it's difficult to pick a cluster in here and then bring up properties about that cluster because it's a three-dimensional space, right? And clicking is inherently more of a 2D operation. But it's easy to click and choose clusters in a tree map and then see where they appear in the 3D space and find out more about them, and so on. These are snapshots from the video we just saw. It's much nicer to see the actual video than just a slide. So now we're going to talk about focus and context visualization. We're going to see lots of examples of this as we go along. So focus and context visualization is all about this scenario when we have too much data and we want to focus on a subset of the data. So, for example, sometimes the data is not of uniform importance, right? Different people will want to focus on different subsets, and so we can use something called focus and context to visualize as a visualization visualization approach. So only if we're trying to separate the important data from the unimportant data, we run into this dilemma. For example, imagine we select we show only the focus, only the important data, right? We run into the dilemma that we might not understand where we are in the data space. An easy example of that is Google Maps, right? When you zoom in on a Google map, what's the first thing you do actually when you see something on Google Maps? Anybody ever use Google Maps? What's the first thing you do?
Direction.
Zoom.
You zoom out,
Zoom
don't
out.
you? You see something on Google Maps and you're like, where am I? And you just hit the zoom out button until you find, oh, I'm in London. Like, that's where I am. And then you zoom back in, right? That's an example of focus. It starts out with the focus, but you're lost in space. So you zoom out to get unlost, find out where you are, and then you zoom in again. That's a dilemma, right? It would be nice if we could have the details that we're interested in, the focus, and the overview at the same time. And someday Google Maps will change, right? It will change to show the focus and context. Someday they will update it and improve it to be a focus and context visualization. Mark my words. I'm using my psychic powers today. It will happen. It will happen. If only the focus is shown, we get lost. If only the overview is shown, we can't see the details. Like exactly if we need to take a left going down, which counting the streets. Can we do both? Can we include both the details and the overview? Right? That's what focus and context is all about. And we'll see lots of details here and examples. Here's an example. This is the context data. So it's 3 line plots plotted over a series of time. But the user has decided to focus in on a subset of time, just these seconds. It gets expanded here, so that's the focus. This is also the focus. So this is a 3D histogram of just this data. But we know where we are in the data from the context. It's an example. You can find a video of that on the DataVis YouTube channel. These are focus and context streamlines. We're going to talk about streamlines later on. These are all the streamlines together, and this is what they look like if the user clicks on a cluster, a certain cluster, and focuses on them, and then the remaining streamlines serve as context. In other words, they're rendered in the semi-transparent way. And here's the user choosing some different clusters with the other streamlines as context. Right? It's difficult to see these clusters of streamlines here, isn't it? But as soon as you can click on clusters and get this clump of swirling lines, while the other ones turn semi-transparent, it's beautiful. These are glyphs for visualizing rugby games. How many people here watch rugby? We're going to see rugby sometimes in this module. How cool is that? I mean, what computer science module lets you like visualize rugby data? That is just amazing. Amazing. You're not going to find that in like databases or programming 101. It's not going to happen. These are focus and context glyphs. So these glyphs are rendered fully opaque. You can see all the details. They're big. And then there are some context glyphs that are behind. And so we can see these special 3 events. They're each visualizing a rugby event in the game. But we can see how they fit in with respect to the other events. These are focus and context parallel coordinates, or it's a style of focus and context. And you might not understand this example yet, but we're going to come back to this. Actually, we're going to come back to most of these examples. The idea is so you understand this concept of focus and context right now. So the focus are the bars, and then these lines serve as context information. That will make more sense the next lecture. These are focus and context graphs. So the user, this is a graph. The user has selected a node in the graph, and then all the edges, these special edges are shown. And these are all the edges that connect the neighboring nodes to each other. And all of the edges are rendered in a kind of semi-transparent grayscale color, but the focus edges are rendered with color and they're fully opaque. We'll look at that example in more detail too. Sort of like a preview of things to come. These are focus and context glyphs. So in this example, this is actually a simulation of an automobile engine. And there's fluid flow coming down into these 2 intake ports. And the user has taken a slice through the geometry, and they've mapped a grid on there. And they've plotted an arrow glyph on at the center of each grid point, right? And that's the focus. The focus is the flow at these grid points, and the context is the geometry. In this case, the actual geometry of the engine, right? If you showed only the geometry of the engine, it wouldn't be very interesting. You couldn't see the flow. If you showed only the flow, you wouldn't know where it was in the context of the engine. So that's combining both. Here's some example on more flow visualization. This is trying to visualize flow with glyphs, right, at the surface. But the glyphs are overlapping, they're cluttered, they're hard to see. Look, it's very difficult to see what's going on there. This is the context information, visualizing the flow as all of the flow, serving as a context. And here we can focus on special points in the flow. So this is combining the focus points of the flow and the context together. So it's a style of focus and context visualization. That will make more sense in future lectures too, because we talk about that. There's another focus and context visualization. Anybody know what that is? Who said that? What's your name?
Manish.
Manish. That's correct. Awesome. What part of the engine?
The central part.
The center. I guess it's near the center, yeah. Yeah, it's near the center. Do you call it gear heads? Is that an auto mechanic?
Yeah.
Is a gearhead? I think that's what they're called. Are there any gearheads in the audience? Does nobody ever like opens up the hood and looks inside, try to figure out what the different parts are? Nobody recognizes this at all? No guesses what that might be? That it's a special looking shape, isn't it? It's very special looking, it's very odd, it's very special, so to speak. Reese?
Where the piston cylinders go?
Yes, where the cylinders for the pistons go inside. Actually, there are 4, right? You can put a piston here, 2, 3, 4, if you wanted to, inside. But that's not the actual pistons themselves. What's around the pistons? Anybody? The pistons are responsible for the combustion. This could be like auto mechanics 101 or something like that. Nobody's looked inside the hood of a car to find out how it works, and nobody has just a vague, rough sort of idea. This is a cooling jacket. So if you don't have a cooling jacket in your engine, it overheats and explodes and you can't go anywhere. So that's what that is. And this is taking a special subset of the fluid flow in that cooling jacket and visualizing it. The fluid flow. So the cooling flow comes in this way. It takes heat away from the pistons and then siphons it off into the cooling system of your car. Has anybody had their car overheat before? That's very common. That's something's going wrong here. This is a focus and context for foam visualization. So it's the same foam as in wash your hands and wash your laundry kind of foam. Right? These are focus bubbles in the foam, and these are context bubbles in the foam. Right? The gray is context and the color is focus. This is 3-dimensional foam. So the focus are these blue spheres, and then the context are the gray scale frame. Any questions? Does everybody think they understand the idea behind focus and context visualization, hopefully? If you want to find out a little bit more, these are references to where we got some of the images from. You'll find the images, all the images that we saw in these papers. You can find them all online. I wouldn't suggest reading them all necessarily because it's too much. But just in case you were thinking, oh, I wonder where that image is from exactly, you could find out with these PDFs. Okay. Let's start the next lecture, because I know you're so eager. You're all so eager. You know how I can tell you're all so eager is because you keep asking, like, can we use bar charts, line charts, pie charts? And you're like, I can't wait to learn more. I can't wait. By the way, the Blackboard thing for third-year students should be resolved. Did anybody notice that the third-year students can now see the Blackboard material? Try to hold back your applause. But anyways, that should be resolved. If anybody has trouble, let us know. So these are more information visualization techniques. So we looked at the hierarchical data, and we looked at focus and context techniques. Now we're going to look at graphs, n-dimensional data, icons, and interaction techniques. So I guess this one's a little bit more jam-packed with material than the previous one. So graphs, let's talk about graphs. Everybody loves graphs, everybody knows what graphs are, right? So this is going to be really fun and exciting. Now, just as a caveat, graphs are a very big topic, very big topic. We could have a module just on graphs. And there is a lecturer in the department that specializes in graphs. And I'm sure he would love to have a module on graphs. And I hope that we do have a module on graphs someday, just on graphs. And there are conferences dedicated only to graphs. Like you can go to a graph drawing conference. Sounds like fun, doesn't it? You can go to mathematical conferences on graphs too, where you don't even see the graphs. They're just defined mathematically. This is a short and convenient introduction. So we're just gonna talk about it for 10 or 15 minutes and introduce the idea. We're not gonna go into a whole semester worth of graph material. So when we produce a graph, or when anybody produces a graph, when one produces a graph, by the way, before I say what the goals of graphs are, what is a graph? Somebody give sort of a definition. Can we define a graph?
It's a
Your name?
Roshita.
Roshita.
It's a graphical representation of given information.
A graphical representation of given information. Okay, that's a start.
Sketch.
Anything else?
Clear view of the information.
A clear view of the information. Yes, that's true. Is that how you would define graph?
Relationships between the information.
Yes, that's right, that's right. I would define it as a set of nodes and the connections that between the nodes, right? That's how I define graph. So you have nodes, and then you have edges, or the connections between the nodes. That's a graph, right? So it's a set of nodes and the connections between them. Very general definition, right? If we want to make a nice graph, how do we make it nice? Like, this is not so nice. I mean, it's kind of nice, but it's not nice in some ways, right? This is nice because it looks kind of nice. Like, I could imagine a decoration. You could hang it from the ceiling. But it's hard to see. There are lots of edges, and it gets sort of tangled up like spaghetti, right? You might have trouble, like, for example, is this node connected to this node? If I asked you that question, it would be difficult to answer in this case, right? So the goals of graphs are to optimize legibility, so-called legibility, the reading of the graph. So there's an optimal length of edges, right? If the edge is too long, it's hard to find, it's hard to follow. If it's too short, it's easy to overlook. We want to minimize edge crossings. So this is a case where there are lots and lots of edge crossings. And the more edge crossings there are, the more difficult it is to read. And we want to maximize edge crossing angles. So the maximum angle we can cross two edges by is 90 degrees, right? If we see edges crossing at 90 degrees, it's easy to follow the edges. If the edges are almost overlapping and the angle of intersection is very, very small, the smaller it is, the more difficult it is to follow, right? So those are the general three optimizations: length of edges, edge crossings, and edge crossing angles. And it's very difficult to optimize all three of those at the same time. It might be impossible. A lot of graph algorithms and graphs focus on just one of them. Say, okay, we're going to do the perfect edge length graph, something like that. So this becomes very challenging when you have large graphs, say hundreds of thousands of nodes or millions of nodes. If you have a graph that's changing over time, very challenging to optimize all these things. If you have a hierarchical graph, the tree is a type of hierarchical graph, the trees that we saw in the last lecture. If we want to put labels on the nodes, that's a challenge too. How do we do that, right? There are labels here. And what about multivariate graphs, another big challenge? Like usually we show univariate graphs. So one variable, for example, people is probably the most common graph where each node is a person. Here's a famous graph. Anybody?
London.
The London Underground, right? It's quite a well known, and I don't remember who made it, but it's gone through a number of iterations to try to improve the layout, right? And you can see that those optimizations, they've tried to apply those rules to the London Underground graph, right? To get the edge lengths, good edge lengths. That's probably so all of the edge lengths, for example, fit on one side of A4, right? That's a nice optimization. You'll notice that the edges are usually intersecting at 45-degree angles or 90-degree angles. That's definitely one of the optimizations, right? And to minimize edge crossings, very challenging in this graph, right? And if they're overlapping exactly, you know it's the same root, right? Now this was done by hand, right? This was not done necessarily by an algorithm. So actually what we want to talk about is how to lay out a graph with an algorithm, not by hand. That's London again, by the way. The satellite view of London. Why do I have the satellite view of London? Anybody, any psychic people here? Actually, everybody is psychic. Can anybody imagine why I have this slide?
It's a kind of visualization.
It is a kind of visualization, yeah. That's right. Does anybody, any other guesses why I might have this slide here?
Geolocation.
What was your name? Lee. What did you say, Lee?
Because the road network could be seen as a graph.
That is right. Yes. Well done, Lee. So this is London. That's one view of London. That's the graph view, and that's London. It's the same. I tried to do it so it's the same area. Well, it's not exact, but it's also London, so to speak, but it's the satellite view, right? That's the graph view and the satellite view. So if I said like if you were in London and you were lost, you came up to me and said, "Oh, I need to get to Buckingham Palace, Bob. Like, can you help me?" And then I said, "Yeah, I have a map. I can help you." And I gave you this. You'd be like, "Okay, that's good, but I have no idea where we are now, and I have no idea where Buckingham Palace is." It's like too much detail. It's too much information. If I gave you this map, you would be happier probably. Oh, I can see we're at like Paddington, and we have to go 2 stops over to, I don't know, Buckingham Palace. I don't even know where it is. You may know which stop it's at. Does anybody happen to know which stop?
Victoria's one.
Victoria? Okay, I don't know. But anyways, if I said you can choose between this map and this map, you would probably choose this map, right? It's difficult to figure out where you are and how to get unlost or to find your way with a satellite view. So here's an there are many, like I said, many graph layout algorithms. This is just an example of an automatic graph layout algorithm. And we're not going to go into the details of the algorithm, but that's from the Many Eyes tools. And what's nice about this example is it's an interactive graph. So the user can just click on a node. So this is how they've solved the connectivity problem. The user can just click on a node, and then all of the connections to other nodes are rendered in a special color, right? So we can easily see, okay, this node is not connected to this node by directly one edge. We can see that immediately, right? So it's an interactive graph. So that's how they approach that problem. Here's some more automatic graph layout algorithms. Does anybody recognize this? Some of you should definitely recognize this. Who recognizes this?
Class hierarchy.
Class.
That's right, from something you've seen before. Who survived my software engineering module? Especially the undergraduate one. This is from Doxygen. So you're all supposed to create these using Doxygen as part of your amazing undergraduate software engineering module. This is amazing. This is an amazing algorithm to lay out a class hierarchy or to show the interactions between member variables and software. Absolutely amazing. I would love to meet the author of that software. Absolutely amazing. Well, authors, and tell them that they do a great job. This one's optimizing for edge crossings. So trying to minimize edge crossings. Really, really amazing stuff. So Doxygen is a tool, for those that you don't know, is a tool you can use to document software, the software you're writing. And it's a tool that you really should use and be exposed to before you graduate, right? But it can generate these graphs of your software and the interactions automatically. It's using a special piece of software to do that. Here's another example from VLSI. Anybody know what VLSI stands for? Does anybody recognize like what it is or anything like that? Yeah, it might be a CPU actually. It might be. It's from electronics engineering, right? Pure some kind of chip. That's right, a motherboard, something like that. The optimizations here are usually minimizing edge crossings again, right? Edge crossings are minimized here. And if edges do cross, I don't know if there are any edge crossings in there. It's not, it doesn't look like it. Doesn't look like it. So that's definitely one of the optimizations that's been applied. It's just nice to see these graphs in the real world, like being applied to the real world. Here's graphs applied to flow visualization, right? So there are two kinds of graphs here. This is a kind of geometric graph that includes the flow geometry, and this is another graph that's abstracted away. But this R1 is the same as this R1, right? And this R2 is the same as this R2, and so on. And look what happens when the graph gets too big. So this graph has not been optimized for anything. But yeah, so that's a challenge. What happens when the graph gets too big? I guess you could say that graph has good edge lengths. All the edges are a nice length, but there are too many crossings and so on. We can also, like I said, this could be its own module. This is just a little kind of idea about some things you can do with graphs. For example, this is in a so-called higher order graph. So in a standard graph, the edges are straight, like this. So we can answer questions like, is there a path from A to B? Yes. Is there a path from A, B to E? You could say, you might start to say yes, maybe, if you go from B to C, from C to D, and then to E. But if you're at E, like, and you're going backwards, you don't know whether, or maybe C is a better example. If you're at C, you don't know if you came from E or from B or from A. Like maybe something traveled from A to C, or maybe it went from like around from E to C, and so on. If you add curves to the edges, you can see a path that traverses more than one node, right? So this is a path that traverses more than one node, so you know if you start here, you're going to traverse this node, and here's another example of a higher order graph edge. And you can apply this to, for example, marine wildlife data, right? If each node represents a behavioral state, in this case flying, diving, and floating, if we just had straight edges, we might not know, okay, given a float, and if an animal was floating, it could have been diving prior to the float, or it could have been flying prior to the float. Right? We can now visualize and distinguish between those two transitions with higher order edges, right? Rather than just straight edges. We can texture map the edges, right, to add information to them, right? So we can add a texture that shows how frequently a transition is made from one node to another, and we can add the direction of the transition through animation. Right. And here's an example that's interacting with the graph nodes. So if a user clicks on a graph node, then the edges are highlighted to the nearest neighbors, right? And they're drawn in color, and then these textures are actually animated to show which direction the transitions, the most frequently transitions are. So this edge, by the way, is very thick, So there are lots of transitions between this node and this, much more than this one and this one, for example. And that just shows a comparison of first order with some kind of third order. Again, this is back to our old problem. If we don't know if there's a transition here from sleep ascent to underwater swimming, right, with these straight edges, it's not possible to tell that. But with curved edges, it's possible to find or visualize transitions that span, for example, more than one node from diving all the way to underwater swimming and so on. Now there is a video of this system if you're interested in seeing actual, like, to see what it's like when it's in motion, so to speak. And the question is, can I find it? Is everybody in full suspense to see, oh, is it possible to find that? I know, I can feel the suspense. There's the cooling jacket, by the way, if anybody's interested in cooling jackets. There it is, smooth graphs for visual exploration of higher order state transitions. This one also has a beautiful voiceover with a Dutch accent. But this just shows what it's like, these graph principles apply to a real problem in a real piece of software with interaction and all these sorts of things. We won't look at the whole thing, but we'll just have a short look. If my laptop ever decides to load it up. There it is. So there are 3 views of the same data. This is the time series view. So this is time along the x-axis, and then the amplitude along the y-axis, and that's the graph view. Right? And then the user interacts with the graph. And they can zoom in on the graph. It might be a little better if I increase the resolution. And the user can click on a node. Okay, so there's the animation, right? Can you see the animation now? There are the higher order transitions. And the user can click on a node and then get the details about the node and the transitions in the third window. Right? It's still loading, that's why it's taking a while. But anyways, if you want to see that whole thing in action, you can watch it on YouTube. I won't sit here and wait for the video to download, because we don't know how long it's going to take. Okay, any questions about graphs? Was that an amazing introduction to graphs? Everybody thinks they understand graphs? It would be very, very interesting to see graphs in assignment 1. That would be cool, very cool. Happy Thursday!
I did it